In this video, I'm going to go over the 5.0 Chemistry final exam practice quiz that covers acids and bases. So this first question here, it says, what is the name of HNO3? So when I am naming an acid, the first thing I look for is if it's binary or not. Binary just means it has two different types of elements in it. So this one is not binary because it has hydrogen, nitrogen, and oxygen. So binary acids start with hydro. So since this is not binary, I'm crossing those out. Next thing you have to look at is the name of the polyatomic ion. This is nitrate, ending in ATE. And when the polyatomic ion ends in ATE, the acid ends in IC. So we end up getting nitric acid. Compare that to the next one down. Again, it is not binary, so I'm crossing out the hydro. Now this polyatomic ion is nitrite, ending in ITE. So that means when we name the acid, it ends in OUS. So we get nitrous acid. HF. Now this one is binary, so I want it to begin in hydro. So I'm crossing out the non-hydro examples. And anytime it is binary, it starts with hydro and it ends in IC. So we end up getting hydrofluoric acid. The next question, it gives us the hydronium ion concentration. It's 0.00001. It asks for the pH. Now for this, sometimes it's easier to think about it as 1 times 10 to the negative fifth. To get the pH, it's negative log of the hydronium ion concentration. And since it gives that to us directly, 1 times 10 to the minus fifth, you could put that in your calculator and you'll get an answer of 5. Now, since this problem, since the number in front of the scientific notation is exactly 1, and this only works if this number is exactly 1, what you can do is you don't even need the calculator. If it's negative log, what happens is this negative 5 just becomes the pH, 5. Now that, again, that's only the case if it's a 1 in front of the scientific notation. If it was anything other than 1, you would have to use a calculator for that. But again, it's just that exponent, and it just becomes positive. Now the other thing you have to watch out for this with pH, since it's a logarithmic scale, we do significant digits different than any way we've done them before. And the way we do it is the number of significant digits in the problem, which is 1 significant digit. That's how many numbers you have after the decimal place. So it becomes 5.0 as the pH. The next couple of problems are pretty quick ones, just like a little bit of terminology kind of stuff. Bases turn litmus paper blue. Bases have a bitter taste and do not react with metals. Acids tend to be sour and they tend to react with metals. Acids have a pH less than 7. So if you have a pH of exactly 7, that is neutral. Anything below that is going to be an acid. Anything above that is going to be a base. Indicators change color in the presence of acids or bases. And that's what we use during titrations. That lets us know when the equivalent or endpoint is. Now the next problem is going to be a longer one. It's talking about a titration. A volume of 9.0 milliliters, so that is of 0.70 molar sodium hydroxide. So that's the volume of the base, that's the molarity of the base. Neutralizes a 35 milliliter sample, so that's the volume of the acid. And we're talking about perchloric acid, and it wants to know the concentration of the acid. Now when you're doing this, first thing you have to do is write out a balanced equation. So sodium has a positive 1 oxidation, hydroxide has negative 1, so that gives us NaOH. Perchloric acid. Now it doesn't have hydro there or anything like that, so it is not binary, which means we need a polyatomic ion. Since this ends in IC, it's talking about perchlorate, which is ClO4 with a negative 1, and since it's an acid, we have that H positive 1. So what's going on with that, now when we put that together, we get HClO4. an acid-base reaction is really just like a double displacement where everything's switching partners. Just remember the positives and negatives go together. So this sodium, that's a positive 1, is going to bond to this perchlorate, that's a negative 1. So you end up getting sodium chlorate, which is NaClO4. And then you have this positive hydrogen bonding to that negative hydroxide. That becomes H2O. Now, since everything is +1 and -1, we don't have to put any coefficients in this to balance it. It's balanced how it is. And we need to make sure we have it balanced because that's going to come up. Now, the reason why I labeled this problem, a lot of times when you're doing this, we're going to end up doing a stoichiometry problem, sometimes people aren't sure what value to start with. And what you end up starting with is the compound that you have both the volume and the molarity of. So for the base, we have the volume of the base and the molarity of the base in the problem. For the acid, we only have the volume shown, and we're solving for the molarity. So that's telling me I have to start with the base, and I'm going to start with the volume of the base specifically. Now, I have to convert 9.0 milliliters into liters. And I'll show you why that is in the next step. So since I start off with liters, I'm going to put liters on the bottom, NaOH. And what's going on here is I'm going to multiply it by the molarity. So that gives me the units of moles per liter. And that's why I needed the volume to be liters. So this 0.70 molar sodium hydroxide, that's what goes here. 0.70 moles per liter of sodium hydroxide. So the liters of NaOH cancel out. Now what I have is moles of NaOH, so I could put that on the bottom. And what I'm going to do in this step is the mole ratio. So I have moles of NaOH on the bottom, and I'm going to end up putting moles of HClO4 up top. Now we get the value for that from the balanced equation. It's 1 mole of sodium hydroxide to 1 mole of perchloric acid. It's a 1-to-1 ratio. So that's why I get this 1-to-1 ratio here. If these coefficients were not 1-to-1, this is the step that would take that into account. So now moles of NaOH cancel out. What I'm left with right now is moles of HClO4. So I'm going to actually, you know what, I don't want to do that yet. So what I'm going to do is the math for this. I'm going to figure out how many moles of HClO4 are in this problem. And that ends up being 0.0063 moles HClO4. Now, what it's asking me for is concentration. And concentration as the units of moles per liter. And I know what the volume of the acid is. So now all I have to do is take this concentration of the acid, divide it by the volume of the acid, but I have to make that into liters because I need the units of moles per liter. And remember, I get the volume from here. It's 35 milliliters, which becomes 0.035 liters. And now when I do that math, I end up getting 0.18 moles per liter of HClO4, which in the multiple choice is just listed as 0.18 molar. All right, so you're doing a stoichiometry problem to figure out this titration. All right, and the pH of a peach, if hydroxide ion concentration is 3.16 times 10 to the negative 11th molar. So there's a couple things we have to pay attention to here. When we do pH, pH is equal to the negative log of hydronium ion. So you have to pay attention that you're doing the negative log of the correct thing. Sometimes people see this and they just go right to negative log of this 3.16 times 10 to the negative 11th, and that's not giving you pH. That's more like POH, which we don't want. We want pH. So we're going to have to figure this number out. And to do that, we end up using this constant, 1 times 10 to the negative 14th, and that's equal to the hydronium ion concentration multiplied by the hydroxide ion concentration, which is given in the problem. Now, the reason why we use this equation when you're working with acids and bases and looking at concentrations, what we get is this 1.0 times 10 to the minus 14th. That is equal to the hydronium ion concentration multiplied by the hydroxide ion concentration. And if you have a solution that is neutral, that means you have equal amounts of hydronium ion and hydroxide ion. Hydronium ion you can think of being as the acid portion, and hydroxide ion as the base portion. So if you have equal amounts for a neutral solution, you would have 1 times 10 to the minus 7th of each of those. And that means it's neutral. You have just as much acid as you have base. When you multiply those, that's where you get this 1.0 times 10 to the minus 14th. So that is the constant that we're end up using over here. Now, if I want to get hydronium ion, all I have to do is a little division here. So the hydronium ion concentration ends up being 3.16 times 10 to the minus 4th. Now, when I look at these numbers, this is hydronium, which is the acid portion. This is hydroxide, which is the base portion. I can tell that peaches are going to be acidic because -4, or having times 10 to the -4, is a larger number than times 10 to the -11. So that's telling me I have more of the acid portion than of the base portion. So more of the acid portion means it's going to be acidic. So now I could do this pH equals negative log of this number. You have to make sure you're doing the right number. So it's negative log of 3.16 times 10 to the minus 4th. And assuming I hit the buttons right on my calculator, I end up getting 3.500. Again, significant digits are different because it's a logarithmic scale. So if this is 3 significant digits, that's how many numbers I need after the decimal point. And that's what we end up getting here, 3.500. So one of the common mistakes with this problem is that you have to figure out the hydronium ion concentration first and then take the negative log of that.